Live from the University of Texas at Austin, the Liberal Arts Development Studios present Essentials of AI for Life and Society. And now, here are your professors, Joydeep Biswas, Don Fissell, and Peter Stone.
Hi, I'm Joydeep Biswas, and welcome back to the Essentials of AI for Life and Society. So far in the course, we've started to see how AI is a set of techniques, computational techniques for solving a variety of problems, similar to how humans would, right? And we've seen how planning and probabilistic reasoning are some of these techniques. And in this week and the next, we'll start to look at machine learning, a family of techniques that is actually driving many of these recent advances in AI. Okay. So to introduce this topic, I'm delighted to introduce Adam Klivans, who is a professor in the Computer Science Department at UT Austin. Adam is the director of the NSF AI Institute on Foundations of Machine Learning and the Machine Learning Laboratory at UT Austin, which makes him probably the most qualified person on campus to introduce this topic. So, Adam, take it away.
Thanks, Joydeep. Yes, I am Adam Klivans. I'm a professor in the CS department, and I am the director of IFML, which is our Institute for Foundations of Machine Learning. And if you go to our website, ifml.institute, you can find out about all the exciting foundational projects that we're doing here at UT related to AI and machine learning. And so as Joydeep alluded to, it's no coincidence that I'll be talking about the foundations of machine learning for today's topic. Specifically, what I want to talk about today is the question of generalization. So when does a machine learning model generalize? Or, simply put, how do we know if a machine learning model that we create on a set of data is going to work well in the future? How can we guarantee its performance on data that we have not seen before? Because what we're ultimately interested in is building some type of program that performs well or predicts well in the future. So in order to explain the notion of generalization, I wanted to start with a simple example. And this type of problem is called a classification problem. So we're going to be taking some data points and classifying them true or false, or +1 or -1. Or as you can see, in this particular example, I want to think about spam detection, which is a common, one of the most commonly studied problems in classification. So for spam detection, what happens? Well, you get an email into your inbox, and whatever email program that you use right now, it makes some automated decision to determine if that email is spam and should be put in your spam folder, or is a legitimate email, it's not spam, and it should go into your inbox. Okay, I think we've all experienced spam filters. Okay, so let's look under the hood a little bit. There actually is something called a machine learning program that's making a machine learning model to try and figure out if it can, in the future, predict whether an incoming email is going to be spam or not spam. And so, typically what happens is the learner, or the machine learning, the person who's building this machine learning system starts off with a training set. What's a training set? Well, it's a set of emails that someone has already told you, whether or not each email is spam or not spam. So it's a big database of emails. So we might have email 1, email 2, email 3, so on. So this is our training set. You can imagine it's a huge database of emails. And associated with each email, someone's already told us, we already know, okay, email 1 is spam, email 2 is not spam, email 3 is spam. You could imagine this training set being the emails that are currently in your mail program, and the ones that you've clicked on or that you've agreed or that are just sitting in your spam folder, those are going to be labeled spam, and the ones that aren't, we could label those not spam. So, what's the goal here? We want to come up with a program, or a function, as I like to call it. Okay, so we're going to look at this training set and come up with some function. And then when some new email comes in, so we'll come up with a function f. And then when some new email comes in, f is going to take this new email m as input, and it's going to output either spam or not spam. And we're just going to hope that F is going to have good performance on new emails that it hasn't seen before. Okay, so that's the setup. We have this training set. From the training set, we're going to run some algorithm and come up with some prediction function F. This is also, these prediction functions or programs, they're also, I'll refer to them also as sometimes classifiers. Sometimes this function is referred to as a model. Sometimes it's referred to as a hypothesis. And like I said, I like to call it a function. But they all sort of mean the same thing. Okay, you're looking at some training set, you come up with this classifier or model or hypothesis or function, and then the function is going to predict things in the future. Okay, so the first step in building one of these functions or building one of these classifiers is to take every email and to associate it with a vector of numbers. Okay, because life is just much easier if we take text or emails and just transform it into numbers. It's just easier to work with. Okay, and so I've done that for you here in a very, very crude way. So we'll assume that sort of red points here are spam, and blue points correspond to not spam. So I should say so there are 1, 2, 3, 4, 5, 6, 7, 8 points here. 4 of them are red, so each one corresponds to an email. So 4 of them are red, 4 of them are spam, and 4 of them are blue, means that they're not spam. And you can see I've associated each email with a vector of numbers. So for example, this email, it has I'm using a coordinate axis, so you can imagine that the origin is over here or something, but it gets coordinates 1, 3. This email gets coordinates 3, 2. This one is 6, 4. This one is 8, 6. The point is I'm taking every email and I'm associating it with some vector of numbers. Okay, and you might ask, well, how did you do that? How did you come up with these numbers that correspond to emails? That's a whole nother lecture that I'm sure someone will be talking about. It's most closely related to natural language processing. How do you take text and embed it or represent it in some way? It's beyond the scope of this lecture, but there are many, many tools for doing this. Okay, so like I said, the goal is to find a model or a function or a classifier that's going to predict well on emails in the future that it hasn't seen yet. Okay, well, what do we have to work with? All we have to work with is this training set, these emails right here. And so as a proxy for this goal, we're going to find a model that does very, very well on this training set. Okay, so this is already a very interesting idea. I would like to find a classifier or a function that does well on emails that I haven't seen before, but all that I have to work with are the emails that I have in front of me that are in my inbox or that are in this big database that I have. And so the best that that's all I have to work with. And so what people do often is that they decide to build a model or a function that actually does well on this particular training set. Okay, and then sort of hope that if you do well on this training set, it means that you're going to perform well in the future. Okay, so finding a model that does well on a training set is a proxy for finding a model that's going to do well on emails that it hasn't seen before. This is a very, very important idea in the foundations of machine learning. And the key concept that I wanted to talk about today is this notion of a generalization gap. Okay? And in words, it is the difference between how well your function does on the training set and how well it's going to do in the future on points that we haven't seen before. Okay, and so I have these terms here, ERR with a hat and ERR. So ERR is error. Okay, so the error of a classifier or a function. There are many ways to describe this, but you could imagine it as the fraction of all emails the H gets wrong. Okay, so imagine that you had a classifier H and you evaluated it on every email in existence, which is impossible to do. There are too many emails to look at. And imagine that you could figure out, okay, which fraction of these emails did you incorrectly label as spam or not spam? Which fraction of the emails did you misclassify? And The accuracy is, of course, 1 minus the error. It's the fraction of all emails that you got right. But this, this error, this is kind of the true error of your classifier, the fraction of all emails that would ever get wrong. As I said, we can't calculate that. There are just too many emails out there. So instead, what we tend to look at is this quantity error h, and this is the fraction of all emails in your training set. So error of h is the fraction of all emails in your training set that h gets wrong. Okay, so two different quantities here. Error without the hat, the little squiggly hat there, that's the true error of h. It's how well it's doing on the entire population of emails, including ones mostly that you haven't seen before. And this error hat of h, which is also referred to as the empirical loss, well, this is just the fraction of emails in your training set that you get wrong. Okay, and that is something that we can calculate. If you give me a function f or a classifier h, I can simply evaluate h on every point in my training set, and that tells me exactly what the empirical error is for that particular function h. I can just look at my training set and calculate it. It's very simple. Just go through each email in your inbox or in your training set and see if h got it right or got it wrong. Okay, and the critical thing, the quantity that we're very interested in is let me kind of highlight it here, is this quantity here, this absolute value of the empirical error of h minus the true error of h. Okay, and this is basically telling you, well, if, how far off is the empirical error from the true error? So if the empirical error is very small, and I know that the generalization gap is also very small, well, then it means that the true error is very small. Okay? And what I'm trying to avoid is a situation where my empirical error, the number of mistakes that it makes on the training set, is small, but the true error, the number of mistakes it's going to make on new examples, is very large. Okay, and that's something called, sorry about that. That's something called, overfitting. It's an important concept in the foundations of machine learning. Overfitting is when, let me just erase this. So overfitting is when the empirical error h is small, but the true error, how well it's going to perform in the future, is large. Okay, this is a very bad situation. You thought that you were doing well, you came up with a classifier in your training set that had small empirical loss, it makes very few mistakes, but in actuality, when it gets new emails, it's going to make many mistakes. So that would mean that the generalization gap is very large, and that would mean that you've done something that is called overfitting. And overfitting is certainly something that we're going to try and avoid, and something I'll be talking about for the rest of this lecture. Okay, so let's try to actually build a model that does well on the training set that's indicated here. Okay, so remember, red is, I think it's spam, and blue means not spam. Okay, so I'm going to come up with a classifier for you. I'm going to create one right now, okay? So here's what I'm going to do. I'm going to define this function f, and I'm going to say f on 1, 3 is going to equal blue. And then I'm going to say f on 2, 5 is going to be red. I'm just defining it this way. F on, I can define the function however I want. F on 3, 2 is going to be red. F on 5, 7 is going to be blue. I think you see what I'm doing here. I'm basically taking every coordinate for each one of these emails, and I'm just telling f to give it the color that it has in the training set. Okay, I'm hard coding all of the values in the training set into f, or f is simply duplicating what's in the training set. And then I'm going to tell f, f on some m, if m is not one of these training points that I've seen before, I'm going to tell f of m to just say spam. Okay, so let me just repeat that. So f is going to match the training set identically by definition. I'm just going to tell it, whenever you see coordinates from a point in the training set, give it the right label. And I'm going to tell f, look, if you get an email that you haven't seen before, just label it spam. Okay? This is a totally well-defined function. It also has the very nice property that it's training error. So error hat of f is equal to 0 because it makes no mistakes on the training set. The fraction of points on the training set that it gets wrong are 0. But I think you can see that the error of f on future emails is going to be large. Why is that? Well, for future emails that it hasn't seen before, it's just going to say spam to all of them. Okay, so it's obviously not a good classifier. It's not a good hypothesis. It's going to take new emails that you haven't seen before, and it's just going to label them spam. Okay, bad idea. But this is already sort of very, very interesting. I mean, like I said earlier in the lecture, all we have to work with is the training set that we were given. And as a typical proxy for coming up with a good classifier, we just try and minimize error on the training set. Here I did that. I completely minimized error on the training set. I got 0 error on the training set. And yet this function is a terrible classifier. Okay? So my point here is that there's much more to coming up with a good classifier than merely getting small error on the training set. Okay, let's try again. So this time, instead of hard coding f to be the value of all the points in this training set, I'm actually going to draw a curve. Okay, so I'm going to depict f graphically by drawing a curve. So I'm going to have it go like this. There. Okay, so this squiggly line is f. Now, how will f classify? So it's clear, so I'm going to say anything kind of below f So anything below f will label spam, which is red, and anything above f will label not spam. Okay, and you can see I've also gotten 0 training error here. I've labeled everything below f spam and above f not spam. That's really good. And then, when I get a new point, let's say I get a new test point, a new email, if it's here, well, it's above f, so I'm going to label it spam. Sorry, I'm going to label it not spam. And then if it lies below f, like if it's here and it's below f, then I'm going to label it not spam. Okay, so it's another legitimate classifier. It's totally well defined for new points. If it's above f, it labels it not spam, and below f, it labels it spam. It's totally fine. So, and it has 0 error on the training set, so it's great. So the only question is, how well is it going to do on new emails that I haven't seen before? And I really have no idea. It looks like some sort of complicated, weird curve, and it seems very difficult to analyze. Okay, so I don't know. So let's try again. So here I have my data again, and I'm going to do something even simpler now. I'm just going to draw a line. Okay, there I drew one line. Okay, this is my graphical representation of f. This is f. It's a line. And so I'm going to say if everything to the right of f is spam, and I'm going to say everything to the left of f is not spam. Okay, so if I get a new point, a new email, and it lies here, then I'm going to label it spam. And if I get a new email and it ends up being here, I'm going to label it not spam. Okay, so that's my new f. Okay, and now we can ask, what is the error of f on this training set? well, now f is actually making some mistakes now. Like it got all of these right on the right side. Okay, labeled all of these correctly, because to the right you're supposed to say spam. But notice that it's making 2 mistakes here. Okay, so the overall error is, how many points do we have? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 points. So the error hat of f, we made 2 mistakes. There are 8 points, so the error is 1/4. Okay, interesting. So, this is the first classifier where we don't have 0 error on our training set. So that's bad. On the other hand, one really good thing about this classifier is that it's super simple. Okay, I think intuitively what was wrong with our first attempt was that we were simply taking the training set and memorizing it. Okay, we were literally writing down, transcribing the training set. And just memorizing your training set probably indicates that you're not doing any sort of, you're not uncovering any kind of interesting patterns, you're not doing what we would think intuitively of as learning. And on this third attempt, we've done something interesting. We've found a very, very, very simple classifier. It's just a line. Okay, so we're not memorizing the training set, but we are coming up with some very simple classifier. And it is the case, as I'll talk about in just a second, that simple classifiers tend to have smaller generalization gaps. So while we are getting some error on the training set, namely 1/4, it's probably the case that the generalization gap is also small, and its true error probably is closer to 1/4. So we're losing something on the error of the training set, but we're gaining a lot in terms of its ability to generalize to emails that we haven't seen before. Okay, and so the really vexing question, I think what we've seen from these 3 examples, is how can we estimate the generalization gap? Just getting low training error is not enough, but maybe if I have low training error and I can get low generalization gap, I'm happy. Okay, and the only really tried and true answer, and even this comes with many caveats, is to have a validation set. What is a validation set? Well, it's a bunch of emails. Let me use the red and blue. So it's a bunch of emails that that the learner, or the learning algorithm, has never seen before. Okay, so imagine that we came up with F, we came up with our classifier, but we stored these other emails in a vault somewhere. No one was ever able to look at them. Okay, so then we create F, we've created our function F, we know what it does on the training set. We want to figure out how is it going to do on emails it hasn't seen before. Well, we're lucky, we have this validation set. We have a bunch of emails that we've never looked at before, that we've never shown to F, that no one's ever seen before. We know they're labeled, we've put them in a vault, we take them out and we say, okay, how well, F, do you perform on this validation set? And that, in many circumstances, although there are some caveats, in many circumstances, that is a good estimate of the true error of F. Okay, so I'll just write that as, I'll just say performance of F on validation set, usually good estimate of true error. Okay, so if you have a validation set, you can use that to estimate the true error of a classifier. Unfortunately, let's imagine that you've come up with a model and you test its error on this validation set. Well, now you've used up your validation set. If you come up with another function that was dependent on how you did on that validation set, well, now it's sort of entangled with a validation set. You can't use it again. You need another validation set. But typically, these validation sets are labeled examples that you would like to use during your training process. So, it's very rare in modern machine learning applications to have a validation set at your disposal. Whenever you have labeled data, You basically want to train with it. You want to give as much information as possible to your learning algorithm to generate that classifier. So it's just not feasible to always have these validation sets lying around. It's a problem. So how can you tell if you're going to have small generalization gap? Well, like I said, every classifier has some notion of description length or complexity. If you're hard coding your training set, then you probably have a high complexity for your model, your classifier. It has to literally write down every single data point and its label. But if your classifier has a smaller description length, you can prove mathematically, with not too many caveats, that you will actually have a small generalization gap. And therefore, it is often preferable to use classifiers, if you can, that are simple. So going back to our span detection example, this first attempt, we came up with some very complicated classifier. It had to have a separate entry for each point in your training set. Second attempt, a little less complicated. It's this kind of weird curve. Third attempt, super simple. It's just a line. It's easy to describe. It's easy to write down. Just has a slope and a y-intercept. No problem. Okay, and so when you're able to come up with a classifier that has a small description length and gets a lot of your training set correct, it means that you sort of compressed your training set somehow. You're able to describe it using something that has a small description length. You've done some compression. You can formalize this and mathematically prove that it will generalize, have a small generalization gap. Okay, the bad news is that, as you've heard and know about from things like GPT-4, modern deep networks have billions of parameters. They're the farthest thing possible from having small descriptions, and yet they still, in many instances, have a small generalization gap. This is often referred to as one of the deep kind of mysteries of deep learning. Why does this happen? It's still a major open problem, and it's a very exciting area of research. Okay, let me briefly talk about, I guess it's time for an Insta poll. Okay, I hope you got that Instapoll question correct. Speaking of validation sets, one other term that I wanted to say is that a validation set is often referred to as a test set, as long as you haven't seen elements in the test set before. With that in mind, let's jump to another Instapoll question. Okay, I hope your empirical error on that Instapoll quiz was 0. Let me finish up by talking about a regression problem. Previously, we've been talking about a classification problem where you're labeling things, spam or not spam, true or false, +1 or -1. Here, let's talk about a problem, a regression problem, where you're actually going to try and assign numbers to training points. Okay, so the example that I have in mind is that we're trying to predict how much a house would sell if it were put on the market. Okay, so we're predicting home prices. So all of these points here are points, houses in some city, and it's data they've already sold, so we have data about how much they sold for. So maybe this house sold for $20. So like 1632 prices. Maybe this one sold for $18, this one for $37. Who knows? But each house here has a dollar amount corresponding to how much it sold for on the open market. And what we'd like to predict is, given a new house, obviously we'd like to kind of figure out how much it's going to sell for. Okay, so one super common technique that's done here, and this is common from statistics, is you do something called linear regression. So you take all of the points that you have for home prices, and you just draw a line that tends to best fit the prices for on your training set. This is our training set. So just eyeballing the points here, it looks like the best fitting line is going to look something like that. Okay? And then if we get a new house that we haven't seen before, we'll just map it to whatever the line tells us to, whatever the line predicts its selling price is going to be. Okay, I guess thinking about this for a second, the way I've drawn this sort of poorly, because as the line goes up, it should be like higher prices. So as to not totally confuse people, let's say this is 40, I don't know, 35, 20, something like that. Okay, so again, right. So let's assume that we're trying to predict home prices, but this time we have some outliers. So we have some houses in our data set that actually had very, very strange selling prices. They were way under what most of the other houses sold for, so I've written them in green. Okay, so if we were to try and draw a best fitting line to this data set, the line used to be something like this. Let me use the right pen. This used to be the line, but now we have these outliers. So instead of drawing a line that looks like this, these outliers are going to push our line to something like that. Okay, and it's kind of unfortunate because we probably should ignore these outliers. They don't really capture typical trends in the market, or at least they shouldn't be able to affect our line so much. And so, again, the big question is, when I draw a line, how do I know that the line is going to fit new home prices well or not well? What's the generalization gap going to be for drawing a line with respect to this data? Okay, and the idea here is, previously we had looked at preferring classifiers that had small description length. Here we're going to penalize lines that have large coefficients. Okay, so in order to draw a line, you could imagine that in order to draw a line that actually got close to these outliers, I had to use really big coefficients of my line in order to make it go all the way down here to try and capture these outliers. So I'm going to have my learning algorithm penalize large coefficients, which means it will sort of tend to sort of ignore outliers. Okay, and this is often referred to as something called ridge regression. So instead of just minimizing, so if I were to just minimize loss on the training set, then indeed I would take into account these outliers, and it would shift my line kind of this way. Okay, but the idea of ridge regression, something called ridge regression, is that you do linear regression, but instead of minimizing just the loss on your training set, you minimize the loss, the sum of the loss plus coefficient size. Okay, so now if I were to take a line and draw it like this, well, maybe its loss would be okay, but its coefficient size would be very large because it had to try and interpolator get close to these outliers. So the idea behind ridge regression is that instead of just minimizing loss on the training set, you minimize something called loss plus coefficient size. And it turns out that if you do something like this, what you can actually prove in some toy scenarios is that minimizing the quantity loss plus coefficient size will outperform, will generalize better than simply minimizing loss. And this is used to great effect in many machine learning systems. I think we should cut to our last Instapoll quiz. Okay, I would like to leave you with two big questions. One thing that I've not talked about is, how do we come up with an algorithm that actually finds these classifiers that have small error on the training set? If you recall, when we were doing spam detection, we found a line that had empirical error 1/4. It got most of the points in the training set right. It was easy to do in 2 dimensions, but most data is very, very high dimensional. And the algorithmic problem of coming up with a fast, efficient way to find these classifiers on your training set that gets small training loss is often very difficult, and it's a very important question. What algorithm are we going to use to find these classifiers? How do we do it quickly? How do we minimize training loss? Big open question for many scenarios is still not very well understood. And secondly, once you have this classifier, how can you certify its performance on points you haven't seen before, on points that might come from test sets that are different from the type of points that you've trained on? Again, a critical question for developing machine learning systems that are robust to noise, that are robust to distribution shift, and that will have small generalization error. So with that, I'll end the lecture.
Come on over.
Should I bring my iPad?
No, unless you want.
Okay.
All right, that was really exciting.
Great to see
Thanks
you.
for that. Yeah.
Yeah.
So the questions have been rolling in, and please keep them coming. I'm going to start with some of the things that have already come in. So
Did anyone ask about my hat?
I'll ask you about your hat. What's up with the hat, Adam?
IFML, ifml.institute, Institute for Foundations of Machine Learning.
Right, there you go. You should go check out the website and
Yeah.
see what it's been up to.
Check it out. Yeah.
Cool. So let's see, Adam, you started out by saying that machine learning can be thought of as a function approximator. And there were 2 early questions when you spoke about this as detecting spam versus not spam. So somebody asked, sometimes I get emails which seem to me like they're almost identically the same or something, and sometimes almost the same email is classified as spam, and sometimes it's not spam, right? So that's one question. And there's a second question which is related to this, I guess.
Well, what was the question there?
Why is it that does that happen?
Okay.
And the second is that when you say that this is a function approximation problem, are they supposed to have a single predictable output for the same input?
Well, those are great questions. For the first question, when you have 2 emails that are very, very similar, remember that the first step in doing classification for these emails is to put them through some type of embedding. Okay? And very often it's the case that this notion of embedding is able to take emails that look similar, but they might differ in one word, And the function that does the embedding is very, very complicated. And so this one difference between words can actually result in vectors of numbers that are very, very different. And that will allow you, in many cases, to discriminate between them.
I see. So like small changes in input make like large differences, essentially.
That absolutely can be the case. And of course, you would like it to be the case, because small word changes in an email can really change the meaning of the email. Yes.
Cool. Okay.
So what was that second question again?
The second question was, do these behave as functions in the sense that a specific input is associated with a predictable output? So are these meant to be predictable? Are these deterministic functions?
Well, that's a complicated question. In many cases, yes, they are deterministic functions. In other cases, your network might output a probability distribution for what values your output might take on. In that case, you may want to sample from that distribution. So a variety of things can happen. But in all of those scenarios, everything that I've talked about can be adapted to the case where you have a randomized function or you'd like to output a distribution. Those are sort of technicalities that you can work out. Maybe you need to use a different loss function.
Okay. So you gave an example of talking about spam versus not spam, and you had this interesting embedding space which was 2 dimensions. Can you shed some light on what would you do if you had more dimensions? What if you have hundreds of dimensions? How do you cope with them?
Well, yeah, that's often referred to. I mean, that's the big problem about that's the big problem, with doing anything in machine learning. It's called the curse of dimensionality. Data that we're very interested in is often super high dimensional. So if you're looking at an image that's 1,000 pixels by 1,000 pixels, you have many, many, many dimensions to work with there. And yes, that is the hope, is that these images, maybe they lie on some sort of lower dimensional space, or the ones that you're interested in lie in sort of a lower dimensional quote unquote manifold. And perhaps that your machine learning algorithm can take advantage of that, or sort of identify some sparse representation for all of that high dimensional data. You can do dimensionality reduction. There are many techniques to try and reduce the dimensionality of your data. That's a very important part of machine learning.
Cool. All right. So you spoke about classifiers, and you spoke about good classifiers and bad classifiers. And clearly, that sounds like a classification problem itself. Can you train a classifier to predict which classifiers are going to be good or bad?
Well, so that's sort of a complicated question, and it's related to something called hyperparameter optimization. So when you have these algorithms that take a training set and spit out a classifier, the algorithm has a bunch of knobs on it, and how you set the knobs will sort of determine how it picks a function based on the training set to output. And yes, you can try and learn how the different settings on the knobs correspond to different functions that are output. Those are often referred to as hyperparameters. You can try and do some black box minimization of these hyperparameters to kind of automatically figure out the right settings to kind of learn which function should be output. That's sort of a meta learning type algorithm. There is also something called meta learning that deals exactly with that procedure. But yes, there are techniques for coping with that.
Right. And I assume that you can also do things like hierarchical stuff, like you break up the problem into different sets of classifiers.
Yes, you can do that too.
All right, so switching to something a little bit less about just the technology and how people use it. So you spoke about training a spam classifier, and you train it and you deploy it. Now the people who are trying to spam you understand your classifier and try to come up with ways of making small word modifications which slip under the cracks and fool your classifier.
Yeah, those are called adversarial examples.
Right. Yes. So how do you cope with this?
We don't have good it's sort of I don't want to say we don't have good methods. We have some kind of empirical methods for defending against that. You can take your training set, you can add noise to all of the points in your training set so that you hope that you come up with a more robust classifier. But I would say that we're in this state where people come up with techniques to make your network more robust to adversarial attacks, and then people come up with cleverer ways to come up with adversarial attacks, and so that's sort of where we are right now.
So it's kind of like a cat and mouse game.
So, yes, it's a cat. That's the phrase I was looking for. I see someone said, how do deep learning model? No, someone go scroll back up there. No, scroll back up. Someone asked, how large should you take what size validation set do you need to estimate the generalization gap? So that's a very interesting question. And if you take my class on learning theory, you will learn all about it.
Cool. So I guess there's a somewhat of an opinion question there, which is being an expert in machine learning, have any of these recent emerging properties of recent discoveries, including like LLM, surprised you? What have you been surprised by?
Well, I think it's surprising how well GPT-4 works. Yeah.
Okay.
We have a question in the audience.
Oh, yes, please.
This is related to the second question you asked at the end. So, like, about how we can certify the performance of models on unseen data.
Mm-hmm.
For that, is random checking something that's used, or is there like a term for that, or how does that work? Like random.
What do you mean by random checking?
Like randomly checking on like certain unseen examples whether or not the model accurately predicted.
Well, yeah. So when you take a validation set, you are choosing new points at random, and then you're evaluating your classifier on these unseen points from your validation set. And as I said, that does give, under some assumptions, namely that your data is drawn IID from some probability distribution, that will give you an accurate estimate of how well that classifier does on unseen points.
Like random checks on like real world examples. Like when you actually use the model like in the real world scenario, you can just like randomly check it to see if it's performing as expected.
Well, typically, see, my point was that typically you don't have samples to randomly check on. You've usually just thrown them into your training set. Where do you get these new samples? There is something called cross-validation that people use to get an estimate for their generalization gap. I didn't have time to talk about it, but how well that works is a bit controversial.
Yeah. So just a humorous comment from someone who took your idea of meta-learning and said, well, I'm just going to do meta-learning on my meta-learning on my meta-learning, and then I'll be the most learning and I'll be king. So I thought it was amusing, so I thought I'd share that. But anyway, so there's another question on your validation set. So you said that generating these new validation sets is hard. And we've seen some examples of generative AI models. Can't we just ask these AI generative models to generate validation sets for us?
Well, it depends on the application. If I have a protein sequence and I want to know how a mutation affects the protein sequence, I will not be able to ask GPT-4 that, and it will not produce a usable answer for me. It does not know.
Okay, that's true. Now going back to your ridge regression example that you had, so you had a scenario where you had some outliers, right? Is it possible to first, so you came up with an algorithm which would try to simultaneously minimize the training loss as well as have a penalty for like large coefficients, right?
Correct.
Instead of doing that, could you do something else where you first try to categorize outliers and then do training on the inliers?
You can. There are algorithms called outlier removal algorithms that will try and remove outliers from your training set first, and then you can perform regression on that. There's also principal component regression where you, PCR, where you first project down to a lower dimension, again, to try and reduce the dimensionality of your problem, and then do regression in that projected space. So there are many things that people try. Mm-hmm. It's just hard to prove things rigorously about these algorithms. It's a big challenge right now in foundations of machine learning.
Right. And you'd mentioned that there's like at least two key properties that we care about, right? So we want good generalization and we want good accuracy.
Right, if you have a classifier that does very poorly on your training set and it generalizes, it's useless.
Exactly.
Right.
So one way that you start talking about reasoning about this generalization gap is thinking about the complexity of these functions. So as a practitioner, how would you balance the complexity of these functions and hence the analyzability and interpretability of them versus the accuracy of these functions?
Well, the classic and basic thing that is done is you take a linear combination of them and you weight one by a parameter, and then you just kind of try a bunch of different parameters, different combinations of those quantities, and see which one seems to do okay. It's more of an art than a science.
Cool. So unfortunately, we're out of time. So thanks again, Adam. And next week, we'll continue machine learning with Professor Ray Mooney.